So first, let me just introduce a few people. You know many of these people who have been contributed in various pieces of what I am talking about. I also want to especially mention Yemin and Tejani, who both having a poster, which are really related, which are in the same spirit of what I'm talking about. You know, it's the next step of what we're doing. Okay. And so, all right. So I put here a bunch of paper on which the work is based. You can have it in the slides. So let me explain a little bit the challenge of what I want to talk about. What's the general challenge? So in machine learning, you're often trying to get your hands on some probability pi that you only know through certain samples. Okay? So I want to know actually what you know is actually maybe a discrete measure, an empirical measure. That's really the object that's given to you, okay, for a certain number of samples. Okay? That's one thing. Another sample that has been discussed in various talks already is that this mythical probability pi that you're after often is thought to be living on some low-dimensional manifold. Okay? I don't want any real manifold here. I don't care. But what I mean, it is not a density, right? It's living on some special structure in space. Okay? So, and of course, you don't know where the manifold is and so on. Okay? So what you're dealing in both case pi and pi, you're dealing with measures which are singular. They don't have densities. Okay? And that's you can't avoid that. On the other hand, many tools that we use that we know from applied maths, like also in optimal transport and gradient flow and Fokker-Planck equation and KL divergence, they really often rely on having a density. Okay? So, so in some sense, the goal of this talk is to build a number of mathematical tools where you can actually use the tools that you know from KL, your KL divergence, but in some sense to modify them a little bit so you can deal with distribution which are singular. Okay? And so the way you're going to do it is by combining tools from information theory, say KL divergence, which is natural in inference, which tool from optimal transport. Optimal transport are very good at building, at moving probability measure without densities. Okay? So I would like in some sense to have use ID from both, and in possible having both of best possible. Okay, so optimal transport has in some sense has also its issue in the sense that it's also very rigid and very okay. So all right. So I want to build divergence and metrics. Okay, and I want in some sense to regularize them. And as we'll see, regularizing in that context, since we deal with convex objects, the proper way to regularize is to use proximal operator. Proximal regularization, as we'll see. Okay, so let me be a little bit more precise here. Okay. So first, let me remind you what KL divergence is, right? You all probably all know this formula. Okay. And the KL divergence is actually jointly convex. It's especially convex in its first factors. Okay. So if your function is convex, then I am obliged to compute its Legendre transform because that's giving me extra informations. So, and the convex duality here is well known. It's known under the name Dansker-Varadhan formula, which gives you which express the KL divergence as a supremum of a set of continuous bounded functions. And of course, you have the dual formula. So these are the convex duality formula. Okay. So the cumulant and the divergence are convex conjugates. Okay. All right. So let me talk a little bit about KL divergence and what are the properties and what are the properties that I like. Okay. So let me motivate also the KL divergence by something called neural estimations, which maybe was first pushed in modern machine learning by a paper by Michael Jordan, and which is really the basis. It's before GANs, right? 2009, 2000 something, which says, well, I'm trying to compute that from data. Okay? So let me replace the soup over continuous functions by a soup over some neural networks architectures. Okay? That's neural estimation of divergence. And so then if I have that, then I can do what I know what to do. Okay? So on top of that, if I work with data, I can replace I can replace that by empirical empirical expectations, right? Empirical measure. And so what I'm doing at the end, I'm just looking at this functional, which I'm optimizing of some neural network architectures. Okay? Now, but I'm supposed to approximate all bounded continuous functions. Now, I can a priori do it with neural networks, but in practice, of course, I cannot, right? It's way too many functions. So, so what's done in practice is to add to that thing a certain number of regularizations. Maybe a penalty terms. You're gonna penalize the weight. There are various ways to do it, okay? By penalizing the weight of your neural networks, or maybe doing a spectral normalization, which essentially, okay? So what I have done is actually replace that by that, okay? But I have done something pretty drastic when I do the regularization. That's kind of my point, okay? So you have changed that thing into another object. And I would like to understand what is this mathematical object, okay? So have you done, okay? And my message is actually you have done very good things to your divergence, okay? And let me try to see what, okay? So another property of scale divergence which you use is that actually, to me, it's a smooth functions, okay? Again, in the first parameter, I think of a smooth functions because it's a smooth function on the simplex of probability measure. In the sense that if I take, if I perturb it, right, I take something in the tangent space, so a measure of mass 0, sign measure of mass 0. So this is again a it should be rho plus epsilon eta, I'm sorry, rho plus epsilon eta. Then if you perturb in a way that you stay absolutely continuous, then you have a derivative, okay? Which is, I will say simply in the sense that you have the Kerr divergence has a variational derivatives. That means simply that means that, right? And it turns out the variational derivative you can compute, it's a log of the likelihood, okay? Variational derivatives. Now, I want you to note something which is going to be important later, is that the derivative, which is that, it's also the maximum of this when you do the Kerr divergence, right? The maximum is attained, maybe not on the maximum is attained maybe not a bounded continuous function, but if you look at the max, it's simply the log likelihood. If you put the log likelihood, you get that, right? Simple computations. So it turns out that the variational derivative is also the maximum of the representation of the Kerr divergence. Okay? All right? This is not a coincidence. Okay? And if I have a functional which has a well-defined variational derivatives, then I can define a gradient flow, as we have talked in various places here before. Okay? Okay, so for me that's a gradient flow. And if you put that the Kerr divergence, then you get your Fokker-Planck equation and you get your usual. Okay? All right? So one of the questions I want to address is that can you build gradient flow or something which looks like a gradient flow, but if your target distribution doesn't have a density, or maybe it's singular, or it's something like that. Right? Can I change that equation to be able to access measures which are singular? Okay? All right. So let me say a quick things about F divergence if you're interested. You can replace F, right? This is for KL. You can replace it by different functions, nice convex function, especially if they are superlinear. And then you have also a very good duality formula, but now for a different, something which replaces the cumulant. But it has all the nice same property as the cumulant, convexity, and you can do everything I say for F divergence, but I'm not going to do anything, and I'm going to leave it for that. But all what I do can be generalized for proper F divergence if you care. Maybe you don't. Maybe you do. Okay, but I don't want to make the presentation too hard. Okay, so let me also remind you a few things about regularizations, right? I learned regularization is that you do you convolve with a kernel, so you do something Fourier. But actually what's here, you need to do a different type of regularization, which is the regularization you should do for convex functions. I mean, I know probably people know that better than I do, right? But this is the infimum convolution of two functions, okay? And you have seen this thing somewhere in your maybe teaching your class, like that's how you make a function Lipschitz, right? How do you approximate a continuous function by a Lipschitz function? You do exactly that. and as L goes to infinity, you converge to that. Huh? So how you make it. Or if you want, if you have a if you have a function which has a minimum and it's not smooth, and you can smooth it out by doing that, and it doesn't change the smooth, and then you can maybe do a gradient algorithm here. Okay. So the infimum convolution is the way to smoothen functions. Okay. And an important property, you also see it in the C transform. If you optimal transport is also a form of regularizations, because you inherit the smoothness from your weight. Okay. The important property is that the Legendre transform of an infimum convolution is the sum of the Legendre transform. Okay, it's a simple property. It's an exercise. You can do it. All right. Okay. So let's try to regularize my KL divergence. So I'm going to do it in the spirit of neural estimations. I'm going to define a divergence dKL gamma, where instead of taking the soup over all continuous functions, I'm going to take a soup over a much smaller set of functions. Okay? All right, I will give you some example of gamma in the next slides. If you have a gamma, there is also a natural object which is associated to it, which is called the integral probability matrix. An integral probability matrix is given by that, right? You measure the distance between two probability measures by taking the soup, the expectation over that set of functions. Okay? Which you can write it like that if you want, right? Which I will use later. So that's called an IPM. Okay? So from the theory of IPM, you know that a good way to do it is you need to get a set of functions which is rich enough, convexity because you want a norm, balance because it makes your life easier, and it should be you should have enough functions to separate points in the probability to be able to distinguish probability measure to have a good matrix, right? So of course, the function which have a Lipschitz constant bounded by L or 1, right, will do the job. Okay? But you see that's a much smaller set than all bounded continuous functions, right? They are nicer and the derivative is bounded or something like that. Just as a remark, people have been doing things similar as I'm talking that using RKHS. Okay? So the French loves RKHS, and there are a bunch of papers which are in the same spirit as we're doing, but using RKHS. So I won't be French today, so I won't do anything. So I will keep Lipschitz. Okay? What you do in practice is actually looking, for example, at the set of better. At the set, so I'm going to do the theory with that, but what we do in practice, in our experiment, is that we look at neural networks with ReLU, right? So it's linear, and you put a spectral normalization, and the spectral normalization essentially put a bound on the Lipschitz constant. Okay? So that's kind of the implementation of that. Okay? All right? And so, as you know, as Paul told me once, right, the KL divergence needs absolute continuity is just because you have T supremum over all bounded continuous functions. So let me explain that, right? And the theorem is that I have defined my KL divergence like that, but I could have defined it in a different ways by taking the infimum over the probability measure of the gamma IPM and the KL divergence. So I could have started from that. So look at, this is really an proximal regularization of the KL I'm doing in probability space with a distance, right? That's a distance, okay? And so, okay? And so the regularized KL divergence is actually a proximal regularization, okay? Also, there's also a duality formula, but I'm not going to use it. And so you still have duality, and you have an improved estimation of that. If you know that phi is regular, then you can replace KL by that, which is tighter. But okay. So let me maybe. The proof is not that difficult. Once you recognize that the IPM, you can write it as a Legendre transform. You put the constant. You do the usual trick in convex analysis. You put the characteristic function to impose a constraint, and it's telling you that the IPM is also a Legendre transform. And then you use that property. And you put the constraint in there, and then you realize it's the Legendre transform of the sum of the two, and then which is this, and you just do your things. Okay? and then you're there. That gives you these relations. Okay. So it's a convex analysis argument. Okay. So far so good. Now once you have this representation as proximal, then you can use all the proximal property, which are you get more out of this proximal property. The simplest is to see that this is bounded by the minimum of the two, right? By just choosing the intermediate to be either of one, okay? Which telling you immediately no absolutely continuity is needed, right? Because you don't need absolutely continuity for that to be finite, okay? So absolute continuity is I don't care anymore. Okay, that's great. By the compactness of the level set of the KL, you also have a proximal operators, which is the one which satisfies them. Okay. You also interpolate between the two in the sense that if you take if you now take your gamma and scale it, right, just dilate it. If L goes to infinity, you recover all the bounded functions, all the continuous functions. Okay. And if you go L to 0, you recover the IPM by scaling properly. Okay? So how do you pick L in practice? Okay, so for us here, thing of the second is you're going to pick L to stabilize the algorithms. And when Yemin, who is preparing our talk, does it, usually we take L to be 1 or 10 or something like that. Right? So you really want to regularize. I don't want to take the limit. And when we take L too large, our algorithms just die. Okay, so it's really regularization. You will see later why it's a good regularization. Okay. So from now on, let me talk only about Lipschitz functions. If you have Lipschitz function, then of course W gamma 1 is also by Kantorovich, is also the one Wasserstein distance. Okay. And what you have a characterization of the optimizer, right? You have these two dual formula. Oops. And you have an optimal mu star here and an optimal phi. And both are actually realized because it's a nice set you optimize on. And there is a relation between the two. Is that the proximal, okay? I think I forgot the normalization here. It should be proportional, but it's proportional to e to the phi star, where phi star is the max, the argmax of that. Okay? The things we're going to compute again, right? Okay. All right. And so this has a very nice interpretation, is that you want to transport a measure and you do it in an optimal way by transporting it as much as you can, and then but also reweighting it also as much as you can. Because once you are in the support, it's much more efficient to redistribute using KL than transport using Wasserstein, which you have to pay a price, right? You have to push it. KL doesn't know any distance, right? You can just go, it's like immediate, right? All right. So a property, and so that ZU maybe is online listening to us. So ZU did that in a recent paper that actually proved this very strong property, is that actually this thing is finite under no condition on pi, which is really surprising to me, right? It works for rho, if rho has a first moment, which is very weak, right? Just one moment. Pi doesn't need to be, pi can be absolutely any measure you want, okay? So in particular, it's in some sense agnostic to what the data is, okay? Which maybe it's good, maybe it's bad, maybe it looks a little scary because it's maybe too agnostic, but I will try to convince you that actually it's a good thing, okay? And I think Marcos will try to convince you even more tomorrow, okay? So the second property is that, right? So the convolution, if you take an inf convolution, you have two functions, and the inf convolution is as smooth as the smoother function of the two. Well, the same case happened here. Okay, is that actually, so KL is smooth, it has a first variation, and actually without assumptions, the gamma KL divergence has also a first variation. But now you're perturbing in directions which are not absolutely continuous, right? So you can perturb in any direction you want. And what it is that it is, you take the supremum, okay? But this is defined only in rho and pi, the support of rho and pi. So it's unique only there. And then you Lipschitz regularize it. or you take the C transform of it if you are. This is defined now everywhere. Okay. And this is the okay. So what you have now, you have a variational derivative as well. Okay. So if you have a variational derivative, then I can write a Wasserstein gradient flow. Of course, I'm not assuming I have density, so this is written in a very weak sense, right? It's a formal computations. But what we did is start from there. Okay. It makes sense. And now what I'm going to write, let's imagine that rho and pi are their empirical measures. Okay. And then let me do an Euler method. Okay. And if I do the Euler method, what do I get? So I'm really writing that with Euler method. Okay. The Euler method of that for empirical measure is that. Okay. Which we call the gradient particle algorithms, GPA. Okay. So you move the particle, so you, right, at every step you compute, you take the maximum here, compute the phi, take its gradient, and you move the particle according to that gradient. Very simple, right? So the velocity, right, the score, I don't know, something like that, right, is essentially the gradient of that phi. Okay? So since you have since an important reason is that since phi is Lipschitz, your algorithm is very, very stable because it's telling you that the gradient is bounded, and so you don't have, in your algorithm, particles don't fly at infinity because their gradient is too big. So it's a very stable algorithm. Okay. Also, the gradient structure, right, that you have here, right, some kind of gradient flow, telling you that the gamma k, will decrease along the path, at least formally. And if you write, so you have some kind of Fisher divergence, which is written in that term, okay? The gradient of phi star, where phi is the maximizer. And if you write it in terms of particle, it's just simply the kinetic energy of the particle, because this is just the velocity of the particle, so it's just the kinetic energy. Okay. All right. So you can monitor, and we do that in algorithms, you can monitor the Fisher divergence, because it's the quantity you can compute, right? To motivate when you converge, right? When you stop moving, that thing is 0. Okay. So there is lots of theory to be done here, lots of math, but we use it as algorithms. Okay. So, okay. All right. So far so good. So this is the philosophy. So let me give you some example. Okay. So I think here we have a Sierpinski carpet which is embedded into a larger dimensional space, right? And so this is the GPA algorithms in actions, right? We started with a Gaussian, something like that, and we use a GPA, and then you see the GPA pushing the particle onto the target distributions. I have here just comparison with other methods, right? If you try to do it, we can do it with various algorithms, with a GAN. We use actually the same divergence, right? You can also do GAN with this kind of divergence, naturally. That's what you do. This is the GPA. This is WGAN. And this is SGM, right? So the diffusion model is... so you see, it's like you're just landing on the target, it's like little helicopters landing on the targets, or drones. Little drones landing on the targets. Okay. We have various, we also played with mist, and so, and let me maybe not say too much. Let me say another things. After ZU proved this very stability things, we'd say, well, why don't we try to actually learn heavy tail distribution with that kind of object, right? Because it's supposed to be robust. And it is, okay? So it does a really good job, and a better job than comparison. We compare it with various algorithms like OT flow and normalizing flow. And then you see the GAN and the GPA are actually doing a really good job in capturing the tail of the distribution as far as you can, right? It's particles. And we had ridiculously heavy tail layers, I think, as far as we can. So I think even tail with one moment, or even without, I don't remember. Okay. So very heavy tails. Okay. And this is in 1D, but we had example in higher D. And so this thing is very, 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 we cannot break it. Okay. So I also want to do a plug for tomorrow's, and I think Yamin is going to give a short talk tomorrow, where she's applying this idea. She has a new paper with Marcos and a bunch of people from Harvard. Well, they add first a force matching component to create a truly generative model, where you really learn the vector field, a global vector field. And they have a very good application in medical data. So I don't want to say anything. I don't want to stall Sanders, but you should go talk to her if you're interested. Yamin has, all the picture I'm doing, yes. Yamin has done them, and she's a great, okay. So what else? Okay. All right. So at this point, let me say a few more things. How much more time do I have? 10 minutes or something? 10 minutes. Okay. So, okay. So, all right. So if you go back, let me go back over there, right? So I can divergence. If I do a regularization here, I can do it, of course, with a norm, right? But I can also do it with a norm square. Okay? So I can try to actually do other type of regularization. Maybe I don't like W1, right? Maybe W1 doesn't have Hamilton-Jacobi HGB, so I should not use it here, right? In this place, right? I should have HGB. I should bring this. So let's try to do that. Okay. And now, once I think in terms of proximal, right? The other case I could start it as a constraint. Now I don't know how to do it, but I can try to do that directly as a. Okay. So let me take simply the weight to be that. You can do general weight, right? And let me take, and if I take I take the inf of a coupling of the distance to the power p, I get the Wasserstein metric to the power p. Okay? All right. And so now I would like to regularize with that things instead of, right? Not p equal 1, but a general p equal 2. Right? Now, it turns out that there is a dual representation of this divergence, which I'm going to use in a minute. So you can write it as a soup over the pair of continuous functions, so that the function of x plus function of y is bounded by the weight, cxy, right? This is a dual representation of the Wasserstein. Okay? All right. So now let me take the proximal Wasserstein divergence, the general one for general weight, where I'm doing the same thing, but I'm going to regularize the KL with the p Wasserstein to the power p. Okay? All right. So what does it give me? Okay. And okay. So it turns out that you also have a duality formula for that. The formula is general for general weight, for general space. Okay, we got the result in great generality. Is that you have here these infimum convolutions, right? That's where I start. And what you have is now you have a dual formula. And the dual formula, you could have guessed it if you think about it, is that now you replace you still have this constraint, phi x plus psi is bounded by that, but now you replace so you see you replace that by that, okay? Which comes from the KL divergence, okay? So you replace this linear function by these convex functions, okay? Risk measure, if you want, okay? And so you can show that the optimizers are unique, and you have the same transport redistribution. Instead now you have a phi and a psi, and of course when you have one, then you know that phi is minus psi, and by Kantorovich-Rubinstein, and you recover the previous formula. Okay, so the same thing. But you have again this. Yeah, I didn't forget the normalizations. You have the same transport redistributions that you optimally transport, and then you optimally redistribute. Okay. I have to say, in many of the algorithms, we mostly use, at least for one, we mostly use that formula rather than we use the proximal regularization to think about what the divergence is and does, but in algorithms we usually use the dual formula. But maybe not always, maybe not. Okay. So let me show you how to prove that. I'm going to do a formal proof. Okay. So you do that. It's some kind of convex argument again. So you take the inf over that, and so you write the dual formula for the WC. So there's a typo here. Okay, and then I'm going to change the inf and the sup. Okay, that's the technical part to do if you want. So let me do it because I want to work. So I do it, and I have that. And then what I'm going to do, I'm going to put the sup over phi. I take the sup of R, and then I use the dual formula, the dual to the Gibbs variational principle, and I just get that. Okay. So what you have is just to justify that. So if you work on a compact state space and C is continuous, then you can actually do a convex analysis, the convex argument, or maybe a minimax theorems, which does it. And for the general case, you do it by a series of arguments, which is kind of pretty reminiscent of one of the proof of convex duality in the first place. So that's the one in Villani's first book, not the one in the second book. Okay? So there is one proof of duality which generalizes in a nice way. Okay? So it's technical, you have to work, but it's not super surprising. Okay? All right? So once you have that, the interpolation property really comes from the fact that you have a proximal operator. So if you scale the weight, if you want, okay, and then you will interpolate again between the two. That's lambda. So you can choose: do you like transport better? Do you like KL better? Right? So I think of it mostly as a regularization of KL, but maybe you want to think of it as a regularization of transport, right? That's up to you. Whatever. In various cases, it will be different things. Okay. And you also have a variational derivatives, which is now has a slightly essentially the same form as before. Okay, we don't have the most general results because there's a technical things I don't know how to do, but we have at least for special case we also have a. Okay. So the take-home message here is that the KL divergence, it does two things. It smoothens the optimal transport, smoothens in the sense that you have a variational derivatives. Okay. And having a variational derivative is really important in machine learning because most algorithms in machine learning do take a variational derivative one way and the other, even if you are living in the neural networks, right? You differentiate with respect to the parameter of neural networks. By the chain rule, you're really doing that too, right? So having that as in the background, if you don't use it directly, I think it's a very good property. It also makes it more convex, right? So think about that. The optimal transport, I want to solve that optimization problems. No, that's okay. The optimal, I have to solve that. That's not very convex, right? Because it's linear, right? It's linear in phi and psi. You have a little bit convexity coming from your constraint, but that's it. This is much more convex. Okay, so you gain convexity in your optimization problem. That's always I think a good thing, right? All right. So the KL divergence, which is convex, right? It's nice convexity. It makes the problem more convex and it makes it more smooth. And the Wasserstein being able to move things which have different supports makes it so we can extend to singular distributions. So that's what I mean best of both worlds. Okay. All right. We have played much less with this divergence than with the first one, right? We just finished that. Maybe there's much more to be done. I just want to make two remarks about implementations. So if you have discrete distribution, you can do the same thing as you do for optimal transport. So that's an optimal transport. That's a simple algorithms to compute this regularized KL divergence between two discrete distributions. You see again, it's more convex, right? More convex than the previous than the original one. And if you have W2, then you can use convex impute neural networks in the same way as you do it for W2, and then everything works in the same way because you have replaced a linear function by a convex function, and that's all what you need, right? And increasing convex functions. And so I've written here, I mean, it's okay. So you can also solve that, compute that divergence for W2, right? That's special for W2 because the C transform is essentially the Legendre transform. You can also do it like that, okay? Right. So, okay. So I think I'm reaching the conclusion. So I want to say one more thing, right? So where is the Hamilton-Jacobi equations? Okay, the Hamilton-Jacobi equation will come tomorrow, okay, in Markov talks. But once you start doing proximal, well, once you do it once, why maybe I want to do it twice? Why, if it works, why should I not do it more? Okay? And so what you can do is, in some sense, and that's maybe very familiar to Lars here, right? Because if you take KL and put W2 now in the representation I was talking about, but in the Benhamou-Bremier formula, then you get a regularization of the normalizing flow, okay? And I think what Marcos will talk a little bit about is, well, I can regularize the KL divergence like that, okay? And so I don't want to say any more, okay? But you can also, there's a connection with flows here and HBG here, which will come tomorrow, okay? And so, okay, that's it. Thank you.